Hello and welcome to another NGen Math 7 lesson by eMathInstruction. My name is Kirk Weiler and today we're going to be doing Unit 2, Lesson 1 on the rational numbers. Now Unit 2 is really all about rational numbers, and rational numbers are more or less every single type of number you've ever experienced, right? Including both positives and negatives. In this entire unit, we're going to be working with signed numbers, numbers that are positive or numbers that are negative, and seeing how they add, subtract, multiply, divide, how they operate with one another. In this first lesson, though, we're really going to be primarily concentrating on just types of numbers, how to plot them, and really how to think also about plotting negative numbers, because that's pretty critical given that they're the newest type of number you've ever had to deal with. Anyway, let's get right into it with the first exercise where we review two very important types of numbers. All right, here we go. Now, like all things that human beings look at and study, when we look at and study numbers, we tend to put them in certain categories. We call them sets in mathematics, and they are put in these sets based on shared characteristics. Now, two of the absolute most important sets of numbers in mathematics are the whole numbers, which start at 0 and then move up by 1 unit each time, so 0, 1, 2, 3, 4, 5, etc. And likewise, the integers, which look a lot like the whole numbers, except they also include negatives that have no fractional part. So negative 11, negative 17, negative 245, negative 1, and it also includes then 0, 1, 2, 3, 4, 5. All right? We're going to be using the terms whole numbers and integers a lot. You'll see the term integer a lot. And mostly when you see the word integer, you want to think about it as a number that could be positive, it could be negative, but it certainly has no sort of fractional parts. There's no 1/2 or 1/10 or anything like that hanging on. Anyhow, let's look at exercise number 1 just so that you can kind of see a little bit of a difference between these two sets of numbers. Exercise 1. One of the following two statements is true. Circle it based on the sets shown above. Choice 1, every whole number is also an integer. Choice 2, every integer is also a whole number. Well, which one of these two statements is true? Logic's a very important part of math, and this gets right down to it. One of these two statements is always true. Think about it just for a moment. All right, well, it's choice 1. Every whole number is also an integer, and you can really see it because we can go over to the integer set and we can find the set of whole numbers sitting inside of the set of integers. There's plenty of integers like -4, -3, -200 that aren't also whole numbers, but it doesn't work the other way around. And again, it's kind of like, the way that, again, when we think about like categorizing something like, let's say, animals, right? You've got animals, and then within those you have mammals, right? And within those you have other categories. So here we have the larger category of integers, and sitting inside that is the category of whole numbers. Anyhow, let's keep moving on and start to look at where these numbers live on number lines. All right, locating integers on a number line. Let's take a look at exercise number 2. We should feel comfortable plotting integers on the number line. Do so with each of the following and label using its letter. Now, just really quick before we kind of get into this, because it's pretty easy, let's be honest. Just kind of a nice review of the number line. Before 5th grade math, from like kindergarten up to 4th grade, all you would have ever seen in terms of a number line was 0 and to the right? That's all you'd have, is this kind of going this way, right? None of this even existed, right? Unless you were paying really close attention to, let's say, a thermometer or something like that, and you lived in a really cold place. Then last year we started to talk about how there could be numbers that are somehow less than 0. And maybe that means they're plotted to the left of 0, right? Or below 0 or something like that. But it's very easy, right? 0, 1, 2, 3, 4, 5, 0, -1, -2, -3, -4, -5, etc. So let's plot some numbers together. This should be pretty easy. Let's plot A and B together and then have you do C and D and E on your own, right? If I have A equals 7, that's simple. 7 is right here, 2 units to the right of 5. On the other hand, -4, right, it would be right here, just 1 unit to the right of -5. Super duper easy. Why don't you pause the video now and plot C, D, and E on this number line. All right, well, one of the most important points on any number line, 0. Oftentimes called the origin, whether it's on a axis like grid paper or on a single one-dimensional number line, the origin, the 0 point is very important. Here's our letter C. Letter D, 12, obviously that's out here, right? And letter E, -10, right there. Simple, right? Especially when we have a nicely labeled number line like that. Now, a very important idea in just general math, physics, science, all of that, is if we have 2 points plotted on a number line, what is the distance between them? And distance is always a positive number. We never talk about a distance of -10 meters or anything like that, right? Distance is a positive number. So let's take a look at exercise number 3, but keep those points up on the board. What is the distance, only a positive number, between letter A, points A and D? All right, well, this is simple enough. And we could literally count, right? Between points A and D, we have 1, 2, 3, 4, 5 units, right? Between A and D, we have 5 units, and literally all we're getting at is that that separates that by 5 units. What I'd like you to do is try to figure out the distance between points B and E and points D and E. Go ahead and pause the video now. Well, B and E are both negative, but it still doesn't really matter. We can look at how many units separate these two. We can see, of course, from -10 to -5, we have 5 units, and another one gives us 6. Now, we don't have any kind of units like inches or feet or centimeters or anything like that because the number line isn't actually labeled with particular units. Finally, D and E, that's maybe the most challenging one because we've got E sitting here at -10 and D is way over here at 12. Right? Now, you could think of it as, well, I've got 10 units here, plus another 12 units there. So there's a distance of 22 units that separates the two. That's it. All right, so just plotting some points, thinking about distance. We're going to eventually have a formula that allows us to calculate the distance between any 2 points plotted on a number line. But that's a little ways in the future. Let's not worry about that for now. Let's keep going and talk about what rational numbers are. All right, a lot of numbers aren't integers, okay? So integers, right, which we saw above, which you've got on your sheet, are, -10, -9, -8, -7, etc., 0, 1, 2, 3, 4. Exercise 4, though, gets at a very important idea, which is that not all numbers are like that. So I'd like you to pause the video right now and see if you can give me 4 numbers that are not integers, and there's a lot of choices. Well, maybe the first number that you ever experience that isn't an integer is the number 1/2, right? When you're a young kid and you're like, how old are you? I'm 4½. Right? Which is really any age between 4 and 5, apparently. I'm 4½, right? You're already looking at numbers that aren't integers. 4 is an integer, 5 is an integer, 1/2 isn't, right? And really, numbers that aren't integers are numbers that have fractional components. So you could just rattle off 5 integers, right, or 4 integers right now if you wanted to. Or if you wanted to, you could get a little bit more fancy and you could give some mixed numbers like 3 1/3. You could even throw a negative in here. You could say, let's put in a negative with a decimal, -4.2, and I don't know, maybe -5/2, right? All of those are non-integers, right? Because they have fractional components to them. Now, let's look at how we define a rational number. All right, a rational number is any number that can be expressed, which means written, as the ratio of 2 integers, right? That's what a rational number is. All rational numbers can be written as fractions, which are ratios, right? It's the numerator to the denominator, right? it's a ratio or a fraction, right, where both of these two things are whole numbers. Or a negative fraction, again, where these are both whole numbers. So it can be written as 3/4, 7/2, -2/3, right? Now, a lot of times people will say, well, rational numbers, fractions, right? You want to be a little bit careful with that, but it's not a terrible way to think about it for now. You may have to expand that definition a little bit when you get into high school. But for now, if you want to think about rational numbers as any numbers that can be written as fractions, that's not a bad way to do it. And that is a lot of numbers. In fact, that's basically every type of number that you've ever seen so far. Let's take a look why. Right? So, placing a number in its rational form. Essentially, every single number you've seen so far has been a rational number. And let's take a look at exercise 5 when we write numbers in their rational forms. For each of the following numbers, write in their rational form, i.e. as the ratio of two whole numbers. All right, in other words, I can take each one of these four and I can actually write it as a fraction. Letter A, which is a mixed number, right? That one, 2 3/5, well, that just means I need to change it back into its improper fraction form. So let's do that together, right? As we well know, 2 is just the same as 10/5. So 2 3/5 is the rational number 13/5. We might say that it's the ratio of 13 to 5. The ratio of 13 to 5, or just 13/5, right? Each one of these three numbers can be placed in fraction form. Pause the video now and challenge yourself to see if you can do that. All right, well, letter B is literally all in the way you even talk about this number. That is the number 7/10, and there's its rational form, right? This is the ratio of 7 to 10, or just the fraction 7/10. This one might be a little bit harder, right? But given our work with decimals, it shouldn't be that bad. 3.87 is the same as 387 to 100, right? That's its rational form. Maybe the trickiest one, but certainly one you've experienced, is when you actually have an integer, like 5 or -2 or 17. If you want to write it in its rational form, this is truly just equal to the ratio of 5 to 1, or if you will, 5/1. And that's it. So every fraction, every decimal, every even whole number or integer can be written as the ratio of one integer to another integer. All right? And therefore, they're all rational numbers that you've seen so far. Eventually, we'll see numbers that are irrational or not rational, but that's far later in this course. Let's take a look at number 7, locating rational numbers. Exercise number 6. Plot each of the following rational numbers on the number line below. So, it is very, very easy to plot integers on number lines because the integers are just sort of laid out there. But clearly, there are lots of numbers on the number line that aren't integers, right? That have fractional components to them. Locating them can be harder depending on the scale of the number line. One thing that's important before we even start to plot this number line is, what does it go by, right? Let's think about that for a second. We have 0 to 1, and there's 1, 2, 3, 4, 5 subdivisions, all right? Each one of these is actually a 0.2 subdivision, and I want you to think about that just for a minute, right? If I have 0, 0.2, 0.4, 0.6, 0.8, 1.0. 1.2, 1.4, 1.6, 1.8, 2.0. So it's almost like we're counting by twos. So it would be like as if this number line was laid out in twos, except it would be 0, 10, 20, 30, etc. Right? Anyhow, let's do it. So together, letter A, -3.4. Well, obviously, here's -3, here's -3.2, and here's -3.4. So right here is letter A. All right. Now, locating B, C, and D can be challenging as well. I'd like you to pause the video and see if you can figure out where they lie, or at least about where they lie. All right, even letter B, 2.5, that's a little bit tricky. I mean, you know it's halfway between 2 and 3. The problem is we have 2.2, 2.4, 2.6, 2.8, 3.0, so it literally lies right between 2.4 and 2.6. So B. Now, 10/3, of course, that's written in its nice rational form, the ratio of 10 to 3, but that makes it awfully hard to locate on here. What makes it much easier is if we change 10/3 into its mixed number form, right, which is going to be 3 1/3. And again, this becomes more of a challenge, not just to write on the board, but also to locate, right? Because here's 3, and there's 3.2. 3 1/3 is 3.3 with that 3 repeated, right? Remember that from the last unit? 1/3 is 0.3 repeated. So 3 1/3 would be a little bit more than 3.2, but less than 3.4. So it'd be right about in here as best as at least I can do it. Now, negative 21/5, you want to think about that just like 21/5. 21/5 would be 4 with a remainder of 1/5, and then just negative. Now, 1/5, that is the decimal 0.2. So, negative 4 1/5, here we're at negative 4, and then each one of these is 1/5, right? We've divided up one unit into 5 portions, so negative 4 1/5 would be lying right there. All right, so just locating numbers on a number line. And you can imagine if we had more than one decimal, if we had 2 decimals, then we'd have to kind of blow the number line up. We'd have to put it underneath a microscope so we could more accurately locate those points. But this is good enough for right now. All right, let's take a look at one last thing that is amazingly important. Knowing whether or not one number is greater than another one, less than it, or equal to it. Now, that is very clear when both numbers are positive, right? Unless you're having a bad day, you're going to know that 7 is greater than 3, right? When both the numbers are positive, it's pretty easy to compare. On the other hand, if you're comparing 2 and negative 10, that's a little bit confusing, right? So the way that we always talk about it is if 2 numbers are plotted on a number line, the one that lies farthest to the right is greater than the one that lies farthest to the left, all right? Now again, when we talk about something like this, 4.99 and 5.01, that's pretty easy, right? 4.99 is less than 5.01, right? Thinking about that number line, right, we'd have 4.99, then we'd have 5, then we'd have 5.01. 4.99 would lie to the left. But here, 4.37 and negative 10.75, that gets a little bit more confusing. So again, I'd like you to think about each one of these 3 and put either a less than sign, a greater than sign, or an equal to sign in the box to make the statement true. And again, if you're confused about it, think about having a number line, right, where you've got 0, 1, 2, etc., negative 1, negative 2, etc., and think about where you'd plot those numbers and which one would lie to the right of the other one. Pause the video now and try to answer this question. Well, 4.37 would lie somewhere out here. Negative 10.75 would lie somewhere out here. So 4.37 is greater than negative 10.75. By the way, every positive number is greater than every negative number. In fact, 0 is greater than every negative number, right? So it's kind of a nice way to look at it. Now this is a little bit confusing, 24 thirds and 16 halves, except keep in mind that the fraction bar represents division. 24 divided by 3 is 8, 16 divided by 2 is 8, so those are equal. Which means that rational numbers can oftentimes look different but be the same, right? Both of these numbers are written in rational form, 24 thirds, 16 halves. They look different, but in fact they both represent the number 8 and therefore are equal. Now finally, negative 1.8 and negative 5.65. Negative 1.8 would lie right about here. Negative 5.65 would lie about here. The one that's lying right here is to the right of the one lying right here, and therefore negative 1.8 is greater than negative 5.65. That's it. All right, let's wrap this up. So in today's lesson, we primarily reviewed integers, whole numbers, right? How we can plot those on a number line. We defined what a rational number is, just any number that can be basically written like a fraction, and how, more or less, all the numbers that we've seen so far are rational numbers. So you got the rational numbers. Within those, you've got the integers. Within those, you've got the whole numbers, etc., right? Work with these ideas and with plotting numbers and deciding greater than, less than, or equal to in tonight's homework. For now, I'd like to thank you for joining me for another NGen Math 7 lesson by eMathInstruction. My name is Kirk Weiler, and until next time, keep thinking and keep solving problems.